Hello everyone. Last week we have learned the Gaussian elimination and the LU factorization, right? Okay, in this section 2, we need some improvement on the Gaussian elimination and LU factorization with partial pivoting. Okay, partial means not globally, right? Just part of rows, and pivoting. Okay, you should know. Firstly, we know what is a pivot, right? Okay, let's review the example at the end of last week. Okay, we show the three matrices, and first the matrix A. Okay, it is 1, 2, 3 first row, second row is 2, 4, 1, and last row is 4, 6, 7. Okay, we perform the Gaussian elimination. Step 1, we find the L1 matrix, the lower triangular matrix, right? Okay, so here the two numbers or multipliers are -2. It is -2 over 1, right? 2 over 1 minus. And -4, it is 4 over 1 minus. It's okay? Remember? Okay, now we use L1 multiply A from left side, then we obtain this matrix, right? However, now you see here, this number is 0, and we know this number is pivot, right? In step 1, this one is pivot. In step 2, this number is pivot. Now, this is 0 pivot. We cannot perform Gaussian elimination, right? Okay, so of course here, we just said last week, without row interchanges, we cannot perform Gaussian elimination. So that means now if we can interchange rows between the two rows, then that means we can select new pivot, then we can perform Gaussian elimination, right? So if we can select a new pivot, this skill means pivoting. Okay, so you know what means pivoting. We choose or select new pivot in the case of 0, 0 pivot or small pivot. It's okay? So this is matrix A. You should understand. Last week we talked about it, right? Okay. So, okay, we don't review matrix B and C. Okay, here. Note that in the procedure, okay, in the general case for Gaussian elimination, okay, we need this number is not 0, right? It is pivot in step obtained by step k-1. So here, AKK is the diagonal element, right? Okay, so we need each step, all the elements on the diagonal are denominators, right? So the feasible condition for Gaussian elimination is all the pivots are not 0, right? Okay, so and also determinant A11, the sub matrix, I here we use I. Okay, so I from 1 to n. First row is A11 to A1I, and last row is AI1 to AII. It's okay. So these are the ordered principal minus of A. Okay. So that means some problems cannot be solved by Gaussian elimination. Okay, just as the matrix A in this case, right? It's okay. So now you see, just by step 1. Okay, now we obtain 0, 0 pivot, or maybe we can consider another example. For example, like this: 0, 1, 2, 1, 2, 3, and 3, 4, 5. For example, 3 by 3 matrix. Okay, now you see this first element is 0, so we cannot use any Gaussian elimination in step 1. It's okay. This is also 0 pivot. The first pivot is 0. Okay, so now another case, even we can use Gaussian elimination by some small pivot. But okay, in chapter 1, do you remember? Because pivots, they are denominators. So if we use a small number as denominators, okay, will cause large error. Okay, small pivot will cause large error. So that is why in this subsection, okay, we want to improve Gaussian elimination and LU factorization, okay, by partial pivoting. Okay, so firstly, you need to understand why we need to improve Gaussian elimination, because maybe there is zero pivot, or even small pivot also will cause errors, big errors. Okay, let's show you another example. Okay, example 2. Let's use 8-digit arithmetic to solve the following linear system by the Gaussian elimination. Okay, now you see, just a 3 by 3 matrix, right? First row, now you see, this number is pivot, right? First pivot, it is not 0, but it is very small number, 10 to minus 8, the power is minus 8, so it is very small number. It is not 0, theoretically, right? But it is very small. Okay, the first row, here, 2 and 3. And the second row, minus 1, 3.712, 4.623. Okay, last row, minus 2, 1.072, 4.643. Okay, we have 3 unknowns, x1, x2, and x3. Okay, right term, just 1, 2, 3. It's okay for you? Now, we want to solve this small linear system, right? Also, by using the Gaussian elimination. However, here, we face the first pivot. It is very small number. Let's see what happens if we just use this small number as denominator, right? Because pivot, we want to obtain multipliers. Okay, we need to use denominator, right? Okay, let's see. Practice solution. Okay, now we put A and B together, right? Augmented matrix. So the last column is 1, 2, 3, the B, right? Okay, here is A. Okay, now the first step, we're using perform the first elimination. That means we use this number as denominator to find two pivots, two multipliers. It's okay for you? So that means we need to multiply for the first row. Okay, we use the first multiplier I write here. It is, remember, minus, it is a ratio, right? Minus a ratio. The numerator is this number, so it is minus 1. Okay? Divided by pivot as denominator, so it is 10 to minus 8. Okay, so minus, okay, disappear, right? Okay, here, denominator is minus 8, so that is 10 to 8. Okay, it's okay, right? This is a multiplier. We use this number to multiply the first row and to the second row. It's okay for you? So, what happens? Okay, of course, the first number, we use 10 to minus 8 multiply 10 to 8. It is 1. 1 plus minus 1. It is just 0. It's okay? So this number is 0. Okay, let's check this number. How to obtain this number? That means we use, I write here, okay? I write here. It is 1 multiply 10 to multiplier, right? 10 to multiplier 10 to 8. And plus to this number. It's okay? Plus to 3.712. Okay, now you should know, in the question, here we use 8-digit arithmetic. What does it mean? it means, because we need to use a float number, right? Okay, we can only use 8 digits, right? So here, that means we compute the addition between the two numbers. We need to use normalized form. Remember, normalized form. So it is 0.2. We write the first number into normalized form. So 0.2 multiply 10 to 9. It's okay? Here is 10 to 8. But here, we move the decimal to the left side, right? Okay, so that means here 0.2, then 8 plus 1, so it is 9. It's okay? And plus, okay, also we need to use, okay, normalized form. And because we consider the addition, so we should use the same power of 10 to 9. It's okay for you? So that means we should use 10 to 9, the same power. So here, then, okay, now you see, because here is just 3, right? 3.712. So let's see. 1, 2, 3, 4, 5, 6, 7, 8. Okay, here I need to move 3, 7, 1, 2 multiply 10 to 9. Okay, let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's okay for you? It's okay? Because I need to write this number 3.712 into normalized form, but by using the same power of 10 to 9, because we consider the addition between the two numbers, we should use the same power. It's okay? So here should be 10 to 9. Then that means we need to move the decimal to the left side. Okay, so here you see. Okay, from here 1, 2, 3, 4, 5, 6, 7, 8, 9. It's okay? So here, then how many zeros here? 1, 2, 3, 4, 5, 6, 7, 8. 8 zeros. Are you clear? Why here we have 8 zeros? Because we need to move decimal so that we have same power 10 to 9 as this one. It's okay? And by the condition, we use 8 digital. So that means after the decimal, we can only use 8 digital. So 1, 2, 3, 4, 5, 6, 7, 8. Here is the 8th digital. So let's see. Because 3 is less than 5, so we have use round down, right? Round down. So that means actually we cannot have these digitals. It's okay for you? Because we can only use 1, 2, 3, 4, 5, 6, 7, 8. 8 digital. So that means compare with this big number, then you know this number is disappear. It's okay? So that means great number or big number, 8, small number. Do you remember in chapter 1? Okay, I show you some rules to avoid accuracy loss. It's okay? One rule, we need to avoid use big number or large number to add small number. Otherwise, big number, large number will eat small number. It's okay, that is why, because here we suppose we can only use 8 digital. So by the same power, okay, 1, 2, 3, 4, 5, 6, 7, 8. 8 zeros, then we cannot use other digitals. So that means this number is changed to 0. Okay, so then we consider the addition, then the result just the same as 0.2 multiply 10 to 9. It's okay for you? So that is why this number is 0.2 multiply 10 to 9. That means we don't change it. We just use obtain the same number as 2, as 2 multiply 10 to 8. It's okay? Okay, so let's consider this number. If you understand this computation, then you can know why here is 0.3 multiply 10 to 9. Similarly, because we obtain this number by using the multiplier 10 to 8 to multiply 3 and add to this number. It's okay for you? So the same result I write here. Okay, that means we use 3 multiply the multiplier 10 to 8 and plus this number 4.623. 4.623. It's okay? So firstly, we need to write this number into normalized form. So it is 0.3 multiply 10 to 9. It's okay for you? Okay, then you can understand what happens later. Similar to this case, because here also decimal, we need to move the decimal to the left side by, here because here is 10 to 9, right? So here also multiply 10 to 9, then here should be 1, 2, 3, 4, 5, 6, 7, 8, and 4, 6, 2, 3. It's okay for you? Let's check. Okay, from this point, this decimal, 1, 2, 3, 4, 5, 6, 7, 8, 9. It's okay? Okay, so here a little unclear, not clear here. Okay, repeat, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9. It's okay for you? 9 to here. So that means we can only use 8 digital 1, 2, 3, 4, 5, 6, 7, 8 zeros. So that means disappear. 4, 8, 4, 6, 2, 3. The 4 digits cannot be used, right? Okay, and again, great number, large number, 8 small number. So the result is just 0.3 multiply 10 to 9. It's okay? So this number. Similarly, that is why here just 0.1 multiply 10 to 9. Because the similar computation, so I omit the detail. That is just 0.1 multiply 10 to 9. It's okay? Okay, so we obtain the second row, okay, by first step elimination. And also we need to consider the last row, the third row. Okay, for the third row, we need to consider another multiplier. Okay, so it is a minus ratio, right? Okay, numerator is just minus 2. And the denominator is just this pivot. So 10 to minus 8. Okay, so it is just, minus positive, right? So that is just 2 multiply 10 to 8. This multiplier is 2 multiply 10 to 8. It's okay? So now we use this multiplier to multiply the first row and add to the third row. It's okay? So this number should be 0. It's okay? Eliminated, right? It's okay? So we need to check these 3 numbers. Okay, so again, let's show you to consider this number, right? Okay, so similar as this computation, we should use this number, right? First row, this number 2 multiply the multiplier. Here the multiplier is 2 multiply 10 to 8. So 2 multiply 10 to 8. It's okay? And plus this number, right? Because we want to eliminate this number. So 1.072. It's okay? Clear? Okay, now we use normalized form. So 2 multiply 2 is 4. So 0.4 multiply 10 to 9. It's okay for you? 10 to 9. From 10 to 8 to 10 to 9. Similar here. Okay, plus again, because here we need to use the same power, so we need to move the decimal to the left side. Okay, so 0.1, 2, 3, 4, 5, 6, 7, 8. We should have 8 zeros. 1, 0, 7, 2. Multiply 10 to 9. It's okay? So we can check from this decimal from here. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's okay? Come here. Right? Okay, again, because we can only use 8 digits, so they are disappear. Right? Again, so the result just 0.4 multiply 10 to 9. It's okay? 0.4 multiply 10 to 9. So this number is checked. Okay, so continue. We can obtain this number. Actually, it is just 3 multiply the multiplier. That means 2 multiply 10 to 8. And plus this number 5.643. Okay, again. So 3 multiply 2 is 6. So 0.6 multiply 10 to 9 plus 0.1, 2, 3, 4, 5, 6, 7, 8. Right? And then 5, 6, 4, and 3. Multiply 10 to 9. It's okay? So again, we can only use 8 digits. So these digits are disappear. Okay? So the result is just 0.6 multiply 10 to 9. So this number is checked. It's okay for you? And this number, now you see the last number, is just 1 multiply the multiplier, 10 multiply 2 multiply 10 to 8. So it is just 0.2 multiply 10 to 9. It's okay for you? Okay, now we checked the 2 rows by the first elimination. We use this very small pivot as denominators, right? For the 2 ratios to obtain 2 great number as multiplier. Then we use this big number, multiply first row, then add to the second row. We use this number, big number, multiply first row, and add then to the third row. Then we obtain the new second row and the new third row by these numbers. It's okay for you? Okay, let's see what happens next step. Okay, let's come to step 2. Step 2, then here, this number is pivot. It's okay for you? Then this number is pivot. Okay, actually, let's see the relation between these 3 numbers and these 3 numbers. How? Okay, let's see. 0.2, 0.4, 10 to 9, 10 to 9. So that means this number is twice of this number. Clear? Okay, let's check these 2 numbers. 0.3 multiply 10 to 9, 0.6 multiply 10 to 9, also twice, and also twice. It's okay? So that means the third row is twice of the second row. Okay, what's mean? They are linear dependent. It means they are linear dependent, right? The 2 rows. Okay, actually, by the second elimination, actually, we will obtain, we don't change the second row. Okay, I show you again. Now you see, the second row, 3 numbers, we don't change them, right? But we will obtain 0, 0, 0 in the third row. Why? Why we obtain 0, 0, and 0? Okay, because now you see, this is new pivot, right? Okay, let's consider here, I write here. Okay, now first, okay, we just only need 1 multiplier, right? The multiplier is a ratio minus ratio, remember? Okay, what is the numerator? the numerator here. This is numerator, remember? Because we need to use this number to animate this number. So this number is numerator. Okay, so numerator is 0.4 multiplied 10 to 9. It's okay? And what is the denominator? The denominator is a pivot, so it is 0.2 multiplied 10 to 9. It's okay? So what's the ratio? It is just minus 2. Clear? The multiplier now it is minus 2. So we use minus 2 to multiply the second row and add to the third row. So that means now you see we use minus 2 multiply 0.2 multiply 10 to 9 add to 0.4 multiply 10 to 9. Then this number is 0. It's okay? And also we use minus 2 multiply this number add to this number, we are obtain also 0, right? Because we know 0.6 is twice of 0.3, right? Also, we use minus 2 multiply 0.1 multiply 10 to 9, then add to 0.2 multiply 10 to 9. The result is just 0, right? Because these three numbers are twice of this number, and the multiplier just minus 2, so totally change to zeros. Are you clear? Are you clear? Okay, now that means by the step 2, we obtain a upper triangular matrix, right? Upper triangular matrix. However, we obtain zeros in the third row, right? Okay, so now you see what happens in the procession. Eating, right? Great number eat small numbers. Great number eat small numbers, right? Okay, so actually now, because in fact the determinant of A, the original matrix, the determinant is not 0. Though this number is very small, but the determinant of A is not 0. So that means the original system has unique solution. Are you clear? That means the matrix A is a non-singular matrix, so the original system has unique solution, right? Okay, however, now you see, here, by the Gaussian elimination, we obtain U and C, but by U, you see, U is singular, because this 3 by 3 matrix is U, right? It has 3 zeros in the third row. So the determinant of U is 0 now, right? Okay, so that means U and C, because also this number is also 0. Then that means we can obtain infinite solutions for Ux equal to C, right? Now we need to solve this new linear system Ux equal to C. But here, because they are zeros, so U and C, Ux equal to C has infinite solutions, because the determinant of C is 0, right? Is 0. Are you clear? Okay, so that means, of course, this is ridiculous, right? The original system has unique solution, but you will obtain infinite solutions by using Gaussian elimination. Okay, so what's the reason? What's the problem? Okay, here, because we use a very small number as denominator, so there happens great number eat small number. It's okay? So the ridiculous results is due to the small pivot. Okay, so this example shows that even the pivot is not 0, but if it is a small number, okay, accuracy loss, right? Accuracy loss. So that means we need to avoid using small number as denominator. So that means small pivot will cause large error. It's okay for you? So I just show you the example by use small pivot. Okay, now you see we will obtain wrong results. Right? Are you clear? Okay, so we need to solve this problem, right? So that means we need to make some improvement on Gaussian elimination by partial pivoting. Okay, so now you understand. Firstly, you should understand what's the problem by using small pivot. So small pivot should be avoided. Okay, so this skill means by using partial pivoting to improve Gaussian elimination. Okay, actually how to choose, that means we need to choose new pivot by using the maximum column pivoting. Maximum column pivoting means, okay, here, in order to avoid small pivot or zero pivot, right? Two cases. Okay, we add a pivoting strategy before elimination. That means for each step before elimination, we need to choose new pivot. Okay, in Gaussian elimination. It's okay? So this means we choose, because we only choose the new pivot in column, in the same column. So that means partial pivoting, not globally, right? Okay, so that is to select an element in the same column, So that means, okay, column pivoting. Okay, column pivoting means partial pivoting. Okay, we select an element in the same column that is below the diagonal, and has the largest absolute value. So that means maximal column pivoting. Are you clear? We need to choose or select a new pivot. Okay, by using the element in the same column below the diagonal, and it has the largest absolute value. Specifically, in step K, we determine the smallest p integer number bigger than or equal to k, such that, okay, here apk by step k minus 1, its absolute value is the maximum in the column, okay, the column k. Okay, k, and of course for each step. Okay, what does it mean? Actually, that means, for example, I just right here, okay, and this diagonal element, okay, so this number is pivot, okay, below it, here, for example, this number I show you just 0.4, 0.5, for example, the pivot. Okay, then here minus 2, 2, okay, minus 2 and 2, for example, 1. Okay, now you see, if below the diagonal element, below the original pivot, here we have minus 2, 2, minus 2, and 1. Okay, by absolute value, by use absolute value, so the three elements, they are same absolute value 2. Then which one should be the new pivot? Here we can choose the smallest. That means here you can choose just this number as new pivot, because we have same absolute values, so you only need to choose one. Okay, so because p means, okay, you say p means the index of row. Okay, so here this number p is just below the diagonal. Okay, so you can only need to choose the first one. So that is, it has the largest absolute value. It's okay? Then we interchange the case row and the pace row. Okay, we use this symbol to denote we interchange the case row with the piece row. Okay, now in this case, no interchange of columns is used. So that means we only interchange rows. We don't interchange columns. It's okay for you? So that is why here we just use partial pivoting. So that means if we use global pivoting, that means we also need to interchange columns. But now in our course, I don't introduce that algorithm. I only introduce you partial pivoting. That means maximum column pivoting. We only interchange rows. It's okay? So that means here, by this example, first step here, this is the original pivot. It is very small. Compare with the two non-elements in the same column. First column, we know -2 has the largest absolute value. You should know absolute value, okay? -2, the absolute value is 2. Bigger than 1 and bigger than this number, right? So that means we need to choose -2 as new pivot. Are you clear? So let's practice. Here, example 3. Now we apply Gaussian elimination with partial pivoting to the system in example 2. Okay, so let's see what happens by using partial pivoting. This is A and B, original system, right? A and B. Okay, now you should know, partial pivoting means before elimination. In each step, before elimination, we need to select new pivot. So firstly, we need to compare the 3 elements in first column. Which one has the largest absolute value? Okay, it's clear, -2, right? -2 has largest absolute value. Okay, so we need to interchange the first row with the third row. It's okay? This symbol means we interchange first row with third row. So E1 interchange with E3. It's okay? Now you see, we move -2, 1.072. Okay, here 5.643. Here 3 to the first row. And we interchange these 4 elements to the third row. So 10 to -8, 2, 3, 1. Are you clear? Just interchange the 2 rows before elimination. Okay, so that is the difference. The difference between Gaussian elimination, the original Gaussian elimination, we use partial pivoting in each step. It's okay? Now, then -2 is new pivot. Okay, let's apply the first elimination. The first elimination, so we need 2 multipliers, right? Okay, for the first multiplier, I write here. It is minus ratio. Remember? Minus ratio. What is the numerator? The numerator is this number, right? So it is -2, -1. And what is the denominator? Is the new pivot, right? The new pivot is -2. Okay, so we know this number is just 0. Minus, 3 minus. So minus 0.5. It's okay? This is a new pivot, new multiplier by using this new pivot. Okay, then we use -0.5 multiply the first row and add to the second row. Okay, then now this number is changed to 0, and this number is changed to 0.3176 multiply 10. Okay, actually, how to obtain this number? Now I write here. That means we use -0.5 multiply 1.072 add to plus 3.72. 2, 1, 2. It's okay for you? Now you see, okay, here we don't have great number add or plus small number, so there is no eating, right? So you can obtain the result. Okay, please, okay, practice by yourself and check, okay? And this number is obtained by use minus 0.5 multiply, okay, this number 5.643 and plus 2 4.623. Then you will obtain this number. Okay, please check. And also, this number is obtained by minus 0.5 multiply 3 plus 2. It's okay for you? So I can show you. It is very simple, right? So it is should be minus 1.5 plus 2. Okay, it is just 0.5. Clear? Obtain this number. It's okay? Okay, we use this new multiplier to multiply first row, add to the second row, then obtain these numbers. And continue. Let's check. Okay, the second multiplier. Also, it is minus ratio. What is the numerator? Numerator is this number because we use minus 2 as new pivot to animate this number. So it is 10 to minus 8, right? And numerator, okay, is still minus 2. Denominator, alright? Okay, denominator is just pivot, minus 2. Okay, so it is 0.5 minus positive, right? Okay, 1 over 2 is minus 0.5 multiply 10 to minus 8. 10 to minus 8, right? Okay, so then let's check, okay? Of course, this number should be 0 because we just use minus 2 to animate this number, okay? And let's check this number, 0.2 multiply 10. It is obtained by 2. How to obtain it? Okay, now you see. We should use multiplier 0. Okay, come back. Okay, 0.5 multiply 10 to minus 8. Okay, this is multiplier, right? Okay, we use it to multiply this number, first row, right? Multiply first row, 1.072. It's okay? Then add to this number, right? Because we use this number to animate this number. It's okay? Okay, so now plus 2. Okay, now you can see here. Actually, because this is very small number. Now you see 0.5 multiply 1 point. Okay, actually it is almost 0.6. Also 0.5 multiply 10 to minus 8 plus 2, right? Okay, so actually this is very, very small number. So again, compare with this small number, 2 is a big number. 2 is a big number. So actually you will obtain, again, large number is a small number. So actually you will obtain 0.2 multiply 10. That is just 2. Okay? So you can practice. Actually, why we have this? Okay, because again, here is a big number because we need to write. Okay, I write here. Okay, we need to change 2. I write 2 here because 2 is 0.2 multiply 10, right? Multiply 10, and here is 0.minus 8. 10 to 0 minus 8. So we need to use the same power, right? we use same power. This power is just 1. Just 1. Here, 0.5 multiply 1. It almost just 0.5. So let's show you plus 0.5 multiply 10 to minus 8, right? Because this product is almost same as 0.5 multiply 10 to minus 8, because this number is almost 1. It's okay? I just show you what happens. Okay? Then here I use almost. Okay? Then now we should use same power. It's okay? We should use same power. So here is 1, here is minus 8. So we need to use 1 as the same power. It's okay? So 0.2 multiply 10 to 1 plus 0.5 multiply 10 to, okay, let's show you. Because here we should use the same power 1, right? Because here 1 and here should be 1. But here is minus 8. So that means here we need to multiply 10 to minus 9. Minus 9 plus 1 is minus 8. Clear? Okay, so that means we need to write this number in normalized form. Okay, so I just show you this number later here. So what happens? Okay, how many zeros? Because 10 to minus 9. 10 to minus 9 means we move decimal to the left side by 9 digits. Okay, so that means 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 5. Okay, multiply 10 to 1. Let's check, okay? From here, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? It's okay, clear? However, we can only use 8 digits. So 1, 2, 3, 4, 5, 6, 7, 8. Here already 8 digits. So after 8 digits disappear. Okay, that means this number is changed to 0 by using the same power of this number. Right? Actually, it is just 0.2 multiply 10 to 1. See? That is why here 0.2 multiply 10 to 1. Okay, I omit 1 here. Clear? Okay, and similarly, you can obtain this number just by 0.3 multiplied by 10. Why here is 0.3 multiplied by 10? That is just the same as, okay, like here, multiplier, right? The multiplier here is 0.5 multiply 10 to minus 8, and multiply this number, add to 3. Okay, so 3 here, compare with this small number. 3 is bigger number, so you will obtain just a bigger number, 0.3 multiplied 10. And also, this number is obtained by 1 to 0.1 multiplied 10 to 1. It's okay? Clear? Okay, now this is first step. Okay, partial pivoting and first elimination in step 1. It's okay? Now, continue. Let's consider step 2. For step 2, okay, remember, before elimination, we need to select new pivot. Okay, we need to compare these two numbers. Okay, this one is bigger than this one in by absolute value, right? Okay, so that means 0.31676 multiplied 10 is just the big largest pivot, right? So we just fix it as pivot. Now we can consider the elimination, right? Okay, so by first elimination, we obtain this result. Now you see, okay, now because this number is already biggest one, right? So we don't need to select other pivot. So we use this number as pivot to eliminate this number. So change it to 0. Then we use multiplier. So I write here. The multiplier is minus ratio. Remember? Okay, numerator is this number. 0.2 multiply 10. Okay. Denominator is the pivot. 0.31776 multiply 10. It's okay? So it is, okay, 10 disappear. So it is just 0.2 divided by 0.3176 with minus, right? Okay, you can practice by yourself. This is the multiplier. Then you use this number, multiply the second row, add to the third row. Okay, then you will obtain 0 here, and you will obtain these two numbers. Okay, then you obtain U and C. Okay, this is a different U from the original example 2. Are you clear? But now the key is here. We obtain non-singular U. Okay, you can compare with the example 2. You see here, by example 2 here, you obtain zeros in the third row, 4 zeros. So that means U and C has infinite solution. But now by using column pivoting, right? Before elimination, we choose new pivot. Okay, in step 1, right? Okay, then here we obtain another U and C. Now you see we don't have all 0 numbers, right? Okay, in this case, we can use backward substitution to solve Ux equal to C, right? Ux equal to C. Then we can obtain, okay, please practice by yourself. X tutor, denoted by X tutor. Okay, 3 numbers, minus 0, 4, 9, 1, 0, and so on. Okay, minus 0.05 and so on. 0.36 and so on. Okay, T means transpose because the X tutor is the X1 tutor, X2 tutor. Tutor means approximate numbers, right? Okay, X1, X3, and 2 and 3. Okay, now we can compare the exact solution of the original system denoted by X. Now you see minus 0, 4, 9. Okay, compare 1, 0, 5, 8, 2. Okay, here 2, 7, but here 0. So only different here, right? You see, good accuracy, right? Good accuracy. 1, 2, 3, 4, 5, 6, 7. We have 7 significant digits, right? For X1 tutor. Okay, check this one. 0.0508867. Oh, very good, right? You see 7 to here, right? 1, 2, 3, 4, 5, 6, 7. Also 7 digits, right? Compare with the exact solution. Okay, last one. 3, 6, 7, 2, 5, 7, 3. Okay, here 3. Okay, here is 9, but here is 8, right? So it is not a significant digital, but here 1, 2, 3, 4, 5, 6, 7 also has 7 significant digits. Okay, so that means by using the partial pivoting, we can obtain good results with good accuracy. It's okay for you? So we just need to add column pivoting before elimination. Then we improve Gaussian elimination. Are you clear? So this is the idea of this subsection.